Okay, just in case. Okay, then, okay, let me start my talk. And my talk is based on recent joint work with Ryo Kanda. And also, the second part of my talk is based on the published paper with Peder Thompson, and where we studied flat cotorsion complexes, and also especially complexes of flat cotorsion modules. The main concern of the paper was commutative noetherian, and in the recent preprint with Ryo, we studied flat cotorsion modules over Noether algebra. So I'd like to today explain some important roles of flat cotortion modules, also as well as the main result of this preprint based on this paper. And the contents of this talk is divided into 4 parts. And I hope I can manage to finish all of the contents, but the main result will be explained in the second section. Okay. And so let me start the first section. So in the first section, or throughout my talk, I mean by a ring, an associative ring with identity, and mod A denotes the class or the category of right A modules. Okay, so as far as I don't mention, my modules are right modules. And flat A denotes the category or the full subcategory of flat A modules. And the terminology of cotorsion originally appeared in the context of abelian groups, where flat modules are torsion-free modules. And the current definition was given by Enochs, and the definition, its definition says that a module M is cotorsion if the first X module for all flat module vanishes. Yeah, the first X module is defined in this way. And I denote by cot A the full subcategory of cotorsion A modules. It is a very classical fact that this pair is a hereditary cotorsion pair, namely, the class of flat A module is the left orthogonal X1 orthogonal subcategory of cotorsion modules. And the class of cotorsion module is, by definition, the right X orthogonal subcategory of the right X orthogonal subcategory of flat modules. Right? And hereditary means that given a flat module and the cotorsion module, all positive extension vanish. Okay. A famous result due to Beacon, L. Bashir, and Enochs essentially says that the cotorsion pair, or they actually prove the cotorsion pair is perfect. Namely, given a right A module, there exists a flat cover. Namely, this is a flat morphism from a flat module. And if there is another map from a flat module, then this map factors through F. So this is the commutative diagram. And if we consider such a lifting map for F, then any lifting map must be an isomorphism. This is the definition of a flat cover. And by Wakamatsu lemma, the kernel of this map F must be cotorsion. So we do have an exact sequence of this form. As a dual, we do have cotorsion envelope, namely, if there we consider if there is a map from M to a cotorsion module, then we have there is a map from CM to C making this diagram commutative. And if we consider Z, then every extending map must be an isomorphism, right? And again, by Wakamatsu lemma, the cokernel of G must be flat. So we do have an exact sequence of this form, right? And the intersection of this perfect cotorsion pair, namely the core of, or sometimes called kernel of the cotorsion pair, is denoted by full cot A. And by flat cotorsion A modules, I mean flat modules which are flat and cotorsion. And here is an important remark for people mainly working on finite dimensional algebra, or more generally, slightly more generally, algebra. So if A is right or left Artinian, then the class of flat modules is precisely the class of projective modules. So flat modules are projective modules. In this case, cot A is nothing but the class of all modules. So the cotorsion pair is of this form. In particular, the class of flat cotorsion module is precisely the class of projective modules under this setup. Okay. And the slogan of this talk is that if we want to treat module-finite algebra over a commutative Noetherian of positive projective dimension, then it's useful, sometimes it's often useful to replace flat modules and projective modules by flat cotorsion module. Okay. And for such modules, Enochs proved a structure theorem, a nice structure theorem for if R is commutative Noetherian. So given an R module, M is flat cotorsion if and only if M is isomorphic to a direct product of TP where P where P runs through all prime ideas of R, and TP stands for sum at the direct periodic completion of some free RP module. So this is the localization of R. And BP stands for some index set or basis set. And this notation means the periodic completion as usual. Okay. And in fact, I will later explain that, I will soon explain that BP is uniquely determined. The cardinality of BP is uniquely determined by M. So in this sense, the description is essentially unique. Okay. So for such module, yeah, M, there are used formula. So if we consider the so-called co-localization at P, then this co-localization corrects all P components where P must be contained by Q, right? And if we consider the periodic completion, then this operation corrects all P components where P must contains Q. So in particular, if we combine the both operations, then we get the single component. And this technique is useful because sometimes we can reduce a proof to some single components when we treat, especially when we treat complexes of flat cotorsion modules over commutative Noetherian. And we may also replace the completion factor by the tensor product, where kappa P denotes the ratio field of the local ring. Then we can recover the cardinality B P in this way. So as I explained before, the cardinality of BP is recovered by this functor. So the vectors, the dimension of the vector space, kappa vector space, is the cardinality of BP. But of course, this index set could be infinite in general. Okay. Okay, then let me move on to the next section where I will explain the main theorem of my recent paper with Ryo Kanda. In the section 2, R denotes a commutative Noetherian ring, and by A denotes a Noether algebra with structure map phi, namely phi is a ring homomorphism such that the image of R is contained in the center of A, and A is finitely generated as an R module. And I should recall the definition of prime ideas in the non-commutative context. A proper ideal, two-sided ideal is called prime if the next condition holds. So given elements A, B in the ring A, if this inclusion holds, then we have that A belongs to P or B belongs to P. And of course, if A is commutative, the ring is commutative, the definition agrees with the classical one in the commutative ring theory. And I will denote by spec A the set of prime ideas of A. And here is a convenient convention. So since the definition is symmetric, so as set, the spectrum of A and the spectrum of the opposite rings coincide. Of course, we should distinguish their structure, but if given a prime ideal P, then we can naturally regard it as a prime ideal of the opposite ring, and I will denote this prime ideal P by the same notation for simplicity. And another important remark is that the structure map induces a map between spectra. This is not so obvious in general if we treat ring homomorphism between non-commutative rings. But in this setup, we do have this map, induced map, namely, if P is a prime ideal of A, then its pre-image is a prime ideal of R. And if we put P as the pre-image of P, then since A is a right R module, so we can localize it, and the localization of P at P is also a prime ideal of this localized ring. And if we consider the quotient ring, then as a right A module, it decomposes into a finite direct sum of copies, NP copies of a simple AP module, namely a locally simple module. And the number NP is uniquely determined by P. I will sometimes use this number later. And for this locally simple module, we may consider the injective envelope, an injective envelope, and I will denote by IAP. And this is an injective envelope taken in the category of A module, while this also coincides with an injective envelope in the category of AP. In particular, this module is P local. Okay. The next theorem is very well known and essentially proved by Gabriel. So there is a bijection from the set of prime ideals and the class, the set of isomorphism classes of indecomposable injectives given by this assignment. Okay. The next is a key notation for our purpose. Given P is a prime ideal of A, put P as the pre-image of P, and I denote by TAP the dual of the indecomposable injective module corresponding to P over the opposite ring. Okay. And the dual is taken by using the injective envelope of R modulo P. And since the both modules are P local, so we may replace R by RP. And if one prefers, then we may also replace RP by the periodic completion of RP. So in this case, so in this sense, what we defined is precisely the matrix dual of this injective module over the local link. And the next proposition explains how TAP looks like. So given a prime ideal P of spec R, we first consider the localized ring and take its periodic completion. So let me denote by AP hat. Then as a right A module, it decomposes into a finite, yes, this is finite direct sum of the TAP and P. And I'd like to emphasize that this TAP is indecomposable as a right module. Because of the definition, we can check that this is indecomposable. So this is a decomposition into decomposition of this module into a finite direct sum of indecomposable projective AP hat module. Okay. In particular, this module is projective AP hat module. And this is, as I mentioned, this is a finite direct sum because prime ideals of A whose pre-image coincides with Q, P is at most exists at most finitely many. So we may, if one prefer, we may replace the direct sum by direct product. Okay. And the next factor is a more general. So if F is flat, and if we consider its localization and completion, then it is flat cotorsion. This factor is when A is R, this factor was proved by Cruzon and Reynolds. This is a classical fact. And I realized that this fact's implication is not so obvious, especially when we treat non-commutative Noether algebra. So I'd like to emphasize this implication holds true also in the non-commutative setup. And the next result is the main theorem of this talk. So it says given a module over Noether algebra, M is flat cotorsion if and only if M is isomorphic to the direct product of periodic completion of a direct sum where BP is some index set, and we consider it the direct sum of copies of TAP. So each module are indecomposable, especially flat cotorsion, right? A module. And in general, taking a direct sum may not preserve cotorsion property, but an important fact is that if we take the periodic completion, then this module is cotorsion and also flat. Okay. Probably, I think it is essentially mentioned here. Okay. And as like the classical case, the cardinality of each BP is uniquely determined by M. So in the classical case, this factor was deduced by using the uniqueness of dimension of vector space. Instead of it, we use Schmidt-Remark-Asmeier theorem, saying some uniqueness of decomposition of especially applied for semi-simple modules. And I'd like to also emphasize that this theorem actually recovers Enochs result, because if we regard A as R, then we may identify the preimage with P with P in this case. And this was the matrix dual of an injective envelope. And by definition, or by the matrix duality, it is isomorphic to the periodic completion of the local ring. And this completion can be removed once we take the completion. And this module appeared in the Enochs theorem here. So our theorem actually recovers Enochs result. Okay. And an important consequence of this theorem is a one-to-one correspondence between the isomorphism classes of indecomposable injectives in the category of left modules, and the isomorphism classes of indecomposable flat cotorsion modules in the category right modules, given by this assignment. Okay. And first, I'd like to emphasize that if R is Artinian, especially A is an Artin algebra, then as mentioned before, this class coincides with the isomorphism class of indecomposable projectives. So the bijection naturally extends the one-to-one correspondence between indecomposable injectives and indecomposable projectives over Artin algebra, right? And another important fact about this map H is that H explicitly realizes a homeomorphism. This is not just a bijection. This can be regarded as a homeomorphism induced by elementary duality for G-grass spectra. So the first class can be regarded as a closed subset of the G-grass spectrum of left module, and the second one can be regarded as a closed subset of the G-grass spectrum of right A module. And existence of such homeomorphism was proved by Ivo Herzog, and his proof doesn't explicitly give what the assignment is, and his proof also treats a more general situation. On the other hand, our proof or our approach actually explicitly realize this bijection, and also we can completely determine the topology of this, especially this class, in terms of the spectra of prime ideas. Okay. If you are interested in such facts and some background on G-grass spectra and elementary duality and this fact, please see my paper with Ryo Kanda, especially section 8. And another fact I should mention is that the module of this form is a flat cover of some non-trivial module. So the module is the direct product of the locally simple module for each P. And if we take the flat cover A, then it coincides with the flat cotorsion module of this form. In fact, according to the definition of TAP, there is a map from here to here, and the map induces the flat cover. Okay, then let me give an example of a Noether algebra and describe some indecomposable flat cotorsion modules and flat covers. So let A be the lower 2 by 2 triangular matrix over R, where R is an arbitrary commutative Noetherian ring. As a right module, this decomposes into these projective A modules. Okay. And the spectrum of A can be written in the following way, where P1 P is a prime ideal of A of this form, and P2 P is a prime ideal of this form, where P runs through all prime ideals of R. And the indecomposable flat cotorsion module corresponding to P1 P is given by this. So this module is the periodic completion of the localized one, RP. And here we have a canonical map from here to the residue field. And in fact, it induces a flat cover. And this one is the locally simple module corresponding to P1 P. On the other hand, P2P, from P2P, we obtain another indecomposable flat cotorsion module of this form. And the corresponding simple, locally simple module is the factor module of this form. And the canonical map from here to here is a flat cover. Okay. So far, do you have any question? No? Okay. Then let me move on to the next section. So here I'd like to explain how derived category can be realized via flat cotorsion modules. And in this section, A denotes an arbitrary ring. Okay. And I will use a cohomological notation, the cohomological notation for complexes of right A module. And a complex X is called semi-flat if X all components are flat, and X is K-flat in the sense of Spartanstein, namely the functor preserves acyclicity of complexes. The terminology itself appeared in the famous unpublished manuscript due to Abram, Foxby, and Harperin. And also, Abram and Foxby used a similar terminology, replacing semi by DZ. And natural reason why semi-flat is used is that X is called flat as a complex if X is acyclic, and cyclic, namely its cohomology modules are 0. Also, its components and all cycle modules are flat. So, and flat complexes are always semi-flat. So this is actually a weaker notion than flatness. But this terminology could be sometimes confusing. So I slightly prefer to call such complexes pure acyclic complexes of flat modules. In fact, pure acyclicity can be independently defined, and the two definition agrees for complexes of flat modules. Okay. And there is a natural notion arising from flatness. X is called semi-cotorsion if all components are cotorsion, and the functor, this functor preserves acyclicity of flat complexes. Namely, if F is a flat complex in the absence, then this complex will be acyclic. And a similar terminology was used by Enochs, Garcia, Rosas in their paper, replacing semi by DZ. And in their paper, the terminology flat complexes also appear. Okay. And a remarkable fact is that semi-cotorsion complexes, the class of semi-cotorsion complexes is precisely the class of complexes of cotorsion modules. For me, this is surprising. So by definition, we do have this inclusion, but their result says that we also have the converse implication. So semi-cotorsion complexes are precisely complexes of cotorsion modules, right? And the next isomorphism is important. So if X is a semi-flat complex and F is semi-flat complex and X is semi-cotorsion complex, then the derived functor can be computed by this home complex. So we have this isomorphism in the derived category. And we suggested, in our paper, we suggested the following terminology. X is semi-flat cotorsion if and only if X is semi-flat and semi-cotorsion. Namely, X is K-flat in the sense of Spartanstein, and all components are flat cotorsion, thanks to this equality. Okay. And the next theorem naturally motivates us to study complexes of, or especially semi-flat cotorsion complexes. If we consider the full subcategory of the homotopy category of complexes formed by semi-flat cotorsion complexes, then we have the canonical map from K to the derived category. And in fact, this is a triangulate equivalence. An important factor was essentially proved by Gillespie about completeness of some cotorsion pair in the category of complexes. And combining it with Stovichev's work, we can actually prove it, but this is still unfortunately preprint. And motivated by Stovichev's work, the authors Zoni, Cortes, Izuriaga, and Estrada proved this fact. And this fact and Gillespie's work allows us to prove this triangulate equivalence. If you are interested in this equivalence, please see the appendix of my paper with Peder Thompson for more details. Okay, then I'd like to move on to the final section. So here I'd like to discuss finitistic dimensions in terms of flat cotorsion modules. Okay. So a recent paper by Ricardo proves that if the derived category of rest modules is generated by injectives, here this denotes the smallest triangulated subcategory closed under arbitrary direct sums, namely smallest localizing subcategory. Then this condition, this equality can imply that the big finitistic dimension conjecture holds for the left this ring, where A is a finite dimensional algebra. So the supremum of this one is finite. And he also explains that injective generation of derived category implies projective cogeneration of the derived category, where colloq proj A denotes the smallest triangulated subcategory closed under taking arbitrary direct products. So namely, the smallest triangulated smallest co-localizing subcategory containing proj A. And this condition itself can imply the big finitistic dimension conjecture holds true. Okay, and my viewpoint is that we may replace proj A by flat cotorsion. And in fact, if A is left coherent, then injective generation can imply that the derived category is cogenerated by flat cotorsion modules. Okay, and in fact, under a mild assumption, every flat A module has finite projective dimension. These two conditions are equivalent. And in fact, one implication always holds. And if we consider a Noether algebra, it suffices to treat only indecomposable ones. In fact, as far as A is left coherent, we can reduce this colloq closure to the colloq closure of indecomposable ones. But especially for a Noether algebra, we know what they are already by my theorem with Ryo Kanda. And considering Noether algebra is important for the next implication. Also, this description is important for me to show the next implication. And for this implication, A is a Noether algebra and R is local, and I only assume that R admits the dualizing complex. And this situation includes the classical case. And in this case, I had to replace big by little because of some specific reason. But if the derived category is cogenerated by flat cotorsion modules, then we have that the little finitistic dimension conjecture holds true for AO. Namely, I had to replace mod A, the large mod, by the small mod. And the reason why I had to replace big by little was that when I checked his proof, I realized that it is important to detect some injective dimension by a single functor of this form at A. And if R is Artinian, then this functor can detect injective dimension of all modules. But in general, if R has positive dimension, this functor cannot detect injective dimension for all modules. So I have to assume this condition. And then the matrix duality sends all finitely generated modules to Artinian modules. And for Artinian module, this functor works well. Namely, this functor detects injective dimension of them. So I was able to modify his proof to this general setup, replacing big by little. And existence of dualizing complex is important to use the Groton extended interpretation of Grothendieck duality given by Iyengar and Krause in 2007, and combining several facts, including some facts about flat cotorsion module, I was able to modify his proof to this setup. But the proof was actually a bit long, so I'd like to omit it. And so let me move on to the next slide. So here I'd like to explain that flat cotorsion techniques allows us to recover some famous result due to Grothendieck and Reynolds, which says that the finitistic projective dimension is at most the true dimension of R. Okay, and such a proof using flat cotorsion module was given by me and Thompson. So I'd like to give a sketch proof of it. And obviously, we may assume that the true dimension of R is finite. And we consider a module M of finite projective dimension and take an arbitrary. And what we want to show is that the X2 module, X2 group vanishes for any I greater than dim R. This is what we want to show. And the proof is actually, makes sense to see how complexes are replaced by semi-flat cotorsion complex. Okay, so we first take a semi-flat resolution of N. Somehow we consider semi-flat resolution of N, not M first. So this is the classical flat resolution. The flat resolution in the classical sense of this one. Okay, and of course this is an isomorphism in the derived category, and existence of a replacement of F by a semi-flat cotorsion complex is already proved by Gillespie essentially. But here I'd like to explain there is a canonical way to replace F by a semi-flat cotorsion complex. Such a technique was essentially already introduced by my paper with Yuji Yoshino. And so the complex X is the totalization of some double complex. And since F is a complex, if we apply some functor, some additive functor, then this is a complex of this one. So we get a double complex in this way. But AI is the direct product of the composition of localization and completion, where P runs through all prime ideas of R having this condition. And the canonical map differential comes from the standard sign rule of check complex. And thanks to this construction, we get a canonical functorial chain map from F to X. And there is a specific reason why I want to call this resolution, this type of resolution, Adelic check resolution. And I'm preparing some paper about it, but today I'd like to avoid it, its detail. But in any case, this is some this construction is an isomorphism in the derived category. And especially this is more precisely a pure quasi-isomorphism, a stronger isomorphism than quasi-isomorphism, stronger one than quasi-isomorphism. And once we obtain such a construction, then we know we can understand what X is. And using Enochs notation, X can be written in this way. And then it is not hard to reduce the proof to showing the vanishing of cohomology module for all I, where XP is the pay component of X, right? Using co-localization and completion, we can get this complex. And if we admit this fact, especially this one is semi-cotorsion, the proof will go in the following way. So this one is a complex of RP module. So we may localize M at P and replace R by RP. Since by assumption, M has finite projective dimension. So especially this is finite, namely MP has finite flat dimension over RP. And by a classical fact due to Auslander and Buchsbaum, if this one is finite, then it is at most the clue dimension of RP, namely the height of P. And it's not too difficult to check this inequality. Also, using flat cotorsion technique, we recovered also this inequality in my paper with Thompson. Anyway, so once we know this inequality, then taking a semi-flat resolution of MP over over R. So we do have a resolution of this one. And since G is semi-flat, and since XP is semi-cotorsion, so we may, as mentioned before, we may remove R. Okay. So this cohomology is isomorphic to the cohomology, this one. And this one is, it is well known that this one is isomorphic to the homoset in the homotopy category. So suspension corresponds to the suspension in this direction. And we know what XP is. The distance from here to here is at most the clue dimension of R. So if we shift XP more than dim R, then clearly this homoset vanishes, namely this cohomology vanishes. So this is 0. So the proof is completed. And I'd like to close my talk by giving the next proposition, which also uses adelic check resolution. If R is a commutative Noetherian ring and A is a Noether algebra, then the supremum of projective dimension of flat right A module is at most the clue dimension of R. And this is a famous fact due to Crusoe and Reynard, especially when R is A. And what this proposition says is that we can extend the classical result due to Crusoe and Reynard to Noether algebra, even A is non-commutative. Okay, that's all. Thank you for your attention.
Yeah, thank you, Tsutomu. Let us, can we all please unmute ourselves and give Tsutomu a round of applause for his wonderful talk, please. Can people hear me?
Yeah.
Okay, thank you. All right, yeah, thank you, Tsutomu, for your talk. Do we have any questions for the speaker now? If you have a question, you can unmute yourself and speak. And alternatively, you can type your question in the chat, of course. I have a couple of small questions and remarks, but I want to wait until other people have asked what they want to ask. Any questions for Tsutomu? All right, let me ask what I wanted to ask. So this main result of your paper with Ryo Kanda, this structure theorem for flat cotortion modules, in there you need a Noether algebra, right? Is there,
Yes.
like, if I were to ask, where exactly do you need the Noether condition, would it be like, is that a stupid question, or do you know exactly, or I mean, can the class of algebras be expanded by any means?
So are you asking if I can remove some assumption from Noether algebra?
Yeah.
I think that for me it would be very difficult to remove something from Noether algebra. Noetherian for both sides is important, but important also duality by some each injective module corresponding to prime ideal of R was also important. So I think for us, the theorem was so far best possible. Yeah.
And also, I mean, this is about a very small remark that you made regarding the projective dimension of flat modules. So what is the, and you said there are some, you need some mild conditions on A. So the only result that I can think of, the most recent one, is by Peter Jorgensen from 2003 or 2, which says that if A is right noetherian, admits a dualizing complex, then anything that has finite flat dimension also has finite projective dimension. Have there been any improvements on that result since 2003 that I don't know of?
Since or before it, for example, if the ring has cardinality at the most,
LFN,
and
LFN,
then the projective dimension of every flat module is
n+1.
Yeah. Also,
but in that case, you need the ring to be commutative noetherian, right? This is the
no,
Simpson result.
I think that was no. I'm not sure, but probably for all ring, I think Simpson explained.
Simpson
wrote such a paper. I'm not sure if Noetherian is important or not, but commutativity was probably not needed.
Okay.
Yeah.
Okay. Yeah. That's some old paper, I think. I just looked it up. It's from 1974. Yeah,
I think
quite
so.
old. Yeah. Okay. Yeah. Thank you.
Yeah.
Any more questions, Professor Tsutomu? And also, I think at least one of your co-authors from the projects that you were talking about is in the audience. I think I saw Peder, but maybe I don't know. Maybe I think I saw. I might be wrong.
Yeah, I'm here.
Oh yeah, hello.
Oh, Peder is here. Oh.
Yeah, it's just a bit early, so. But I'm here.
Thanks.
Yeah, thank you for coming. I actually I had invited Peder for a couple of other seminars in the past few weeks, but I just realized a few days back that I was sending my emails to the wrong email address. Like I think, I mean, Peder, you used to be at NTNU, right? For
that email doesn't work anymore. So I'm currently out in upstate New York. So you can find me there.
All right. If we don't have any more questions for Tsutomu, let us give him a round of applause again, and I will prepare for my talk. Okay.
Thanks.
Yeah, this is the confusing thing with uploading people over Zoom. I just realized that the smarter way of doing it is just doing it with that hand sign. Yeah.